All right, ready to dive into some pretty intense stuff today.
Always up for a challenge.
Good, because today we're tackling Frege's theorem.
Ah, Frege. A classic.
And this one I think it'll resonate especially well with you, given you're the philosopher and all.
I appreciate that.
The big question here is how Frege went about proving that arithmetic is essentially, like at its very core, rooted in logic.
Ambitious, to say the least.
It really is. It's like trying to show that 2 plus 2 and equal 4 isn't just some, observation we make about the world, but a truth that's like woven into the fabric of logic itself.
You've captured it perfectly. That's the essence of Frege's project, to show that all those arithmetic truths, they can be derived from pure logical principles. It's a view known as logicism.
Oh, okay, logicism, I like it. But to get there, to even attempt this, Frege had to grapple with a really fundamental question, right?
Absolutely, and it's a question that has plagued philosophers for ages.
Which is,
How do we even grasp the concept of number in the first place? How do these abstract entities, these numbers, become given to us?
it's like asking how do numbers, like, come into being? How are they given to us?
Precisely. And that's where things get really interesting. Frege developed two logical systems to try and answer this question: Begriffsschrift and Grundgesetze.
Ooh, two whole systems.
Two incredibly complex and fascinating systems. But there's a snag. The latter, Grundgesetze, unfortunately runs into some inconsistencies. You're familiar with Russell's paradox.
Ah, yes, Russell's paradox, that set theory brain twister.
Exactly. That's where Grundgesetze stumbles. But for our deep dive today, we're going to set that aside and focus on Begriffsschrift.
Smart move.
Because within Begriffsschrift lies a true gem, Frege's theorem.
Sounds promising. So this Frege's theorem, what's it all about?
Well, it's a bit tricky to explain without getting into the weeds, but essentially it shows how, using a specific principle, we can actually derive those foundational axioms of arithmetic, the Dedekind piano axioms. They're like the basic truths, those self-evident things about numbers that we just take for granted.
Right, the axioms. Okay, so to understand this theorem, where do we even begin?
We begin with a journey into the realm of second-order logic.
Oh, second-order logic. That's always sounded a bit more mind-bending than your average logic system.
It can be a bit more abstract, that's for sure. While first-order logic deals with objects, second-order logic allows us to talk about concepts as well. Think of things like properties or relations. It's crucial for understanding Frege's whole project.
So, like, instead of just saying Socrates is wise, we can actually talk about the concept of wisdom itself.
Exactly. That's the beauty of second-order logic. And Frege's system, it goes even further. It focuses on functions and their courses of values instead of sets.
Hold on, functions and courses of values. I'm already feeling a little lost.
It sounds complicated, but think of it like a vending machine, okay? You put in a coin, you get a specific snack.
Okay, I can visualize that.
So the course of values is like a list of all the possible coin inputs and their corresponding snack outputs. For Frege, the extension of a concept, it's similar to this course of values. It captures everything that falls under that concept.
So instead of sets, we have these extensions.
Interesting. Exactly. Now, there's a principle in his system, though Frege never explicitly formulated it, called the comprehension principle for concepts. Basically, it guarantees that for any describable property, there exists a corresponding concept.
So if we can describe, say, the property of being a cat lover who enjoys podcasts about logic, boom, there's a concept out there for that.
You got it. It's a pretty powerful principle when you think about it. Now, there's this other piece of the puzzle, basic law V in Frege's system. It attempts to formally link concepts and their extensions. But as we know, this is where things get a bit tricky.
You mean with Russell's paradox?
Precisely. That's where the inconsistencies crop up, throwing a wrench into the whole system. But we'll get to that later. For now, let's stick with how Frege approached those cardinal numbers, the ones we use for counting.
Okay, yeah, good plan. Let's dive into numbers.
Here's where Frege makes a brilliant and somewhat counterintuitive move. He argues that statements about number, they're actually statements about concepts. Like when you say there are 7 cats napping on that couch, you're not just talking about the number 7, you're talking about the concept of cats napping on that couch.
So the number is somehow bound up with the concept.
Exactly. It doesn't exist in isolation. To really solidify this idea, he introduces the concept of equinumerosity, represented by the symbol A. It basically means that two concepts are equinumerous if there's a one-to-one correspondence between the objects that fall under each concept. It's like pairing things up. If every item in one group has a unique partner in another, they're equinumerous.
Like matching socks. If I have a pile of, say, 7 socks, and I can match each one to a different shoe, then the concept socks in the pile and shoes I'm matching, they're equinumerous.
Perfect example. You got it. Now, this leads us to Hume's principle, a fundamental concept in Frege's work. It states that the number of f's is identical to the number of g's if and only if f and g are equanimous.
Okay, so basically if I can pair things up 1 to 1, they have the same number.
Exactly. And this becomes Frege's way of defining the number of f's, but not directly, contextually, right? Instead of saying what a number is, he's telling us what it means for two concepts to have the same number.
It's like defining equal before you define number. Feels a little backwards.
You could say that. Frege did actually try to define the number of f's more directly using extensions, but that approach, well, remember those inconsistencies we mentioned.
Right, Russell's paradox strikes again.
You got it. That's where the direct definition approach falters. But the cool thing is, Hume's principle itself remains a powerful and consistent idea.
Okay, so even without pinning down number precisely, he can still work with his principle to build up his theory of arithmetic. That's impressive.
It is, and to do this, to build this theory, he has to go even deeper into the structure of numbers. And this is where his analysis of predecessors and ancestrals comes into play.
Now, when I hear ancestral, I think like family trees. Are we talking genealogy here?
Not quite family trees, but you're on the right track with the idea of connections and relationships. Remember, we're dealing with concepts and relations. Think of a relation like X is taller than Y. We can extend that across a whole group and say things like X is the tallest.
Okay, so we're going beyond just comparing two things. We're looking at how they relate within a whole series.
You're getting it. Now, Frege, he starts with the relation X perceives Y, meaning Y is one more than X.
Right, so like 4 precedes 5.
Exactly. Then he defines the ancestral of this relation, written as X precedes Y, which basically means X comes before Y in the number sequence.
So 3 precedes 4 and 3 precedes 5 because it comes before 5 in the sequence of like natural number.
Precisely. You're getting the hang of this. But it gets even more nuanced. He then introduces this idea of the weak ancestral, written as X precedes plus Y. This one means either X precedes Y or X equals Y.
Okay, so if 3 precedes 5, then 3 also precedes plus 5. And 5 precedes plus 5 because it equals itself.
You're nailing it. And this precedes plus relation, it's absolutely central to how Frege defines natural number.
Oh, how so?
He defines a natural number as being a member of the precedes series starting from 0. So any number that you can reach by starting at 0 and repeatedly adding 1, it fits the definition.
So like 1 is a natural number because you get there from 0 by adding 1 once. And 2 is a natural number because you add 1 twice. Got it.
Precisely. And the amazing thing is, from this definition, Frege manages to derive those famous Dedekind-Peano axioms, the building blocks of arithmetic. You know, those axioms that state things like 0 is a natural number, every natural number has a successor, and so on. He essentially constructs this entire system of arithmetic, all based on Hume's principle.
Wow, that's mind-blowing. Starting with just this concept of equinumerosity and this contextual definition, he manages to build this whole system of natural numbers. It's pretty amazing. I'm starting to see why Frege is considered like a giant in the field of logic.
He truly revolutionized how we think about the connection between logic and math. But, as you might imagine, a project this ambitious, well, it doesn't come without its philosophical baggage.
I bet. Thinking about deriving arithmetic from logic, it just makes you think, like, are numbers then just logical objects? And what does that even mean? It makes your head spin.
It definitely raises some heady questions, and that's what we'll dig into in the next part of our deep dive. Welcome back. Before our little break there, we were talking about how Frege, he actually managed to derive the foundations of arithmetic just from Hume's principle.
It's pretty wild, right? It's like the sheer elegance of it all. Building this mathematical, I don't know, this grand cathedral and using logic as the blueprint.
It's a powerful demonstration of what logic can do, that's for sure. And from those Dedekind-Peano axioms we talked about, you can go on and derive all sorts of other arithmetic truths, like addition, multiplication, all the operations we use all the time, they come from those basic axioms.
It's pretty incredible when you think about it. But I gotta say, since you, dear listener, are a philosopher, I'm guessing you're probably like itching to dig into the philosophical implications of all this. Like, if we derive arithmetic from logic, does that mean numbers are just logical objects? What would that even mean? It's enough to make your head spin.
Yeah, no, it's a heady concept for sure. Frege was really challenging this idea that our knowledge of math comes from, intuition or sensory experience. He was saying, no, we can grasp mathematical truths through pure reason alone.
So is he saying that numbers exist in some, like, abstract realm of pure logic, completely independent of the physical world.
That's one way to interpret it, yeah. It definitely pushes back against a Kantian view that math requires some kind of, intuition, like our spatial understanding for geometry.
Huh, interesting. So for Frege, numbers aren't grounded in our experience, they're grounded in the structure of logic itself.
Exactly. But here's where things get even more interesting philosophically speaking. Even if we accept Frege's theorem, right, we're still left with this big question. How do we know that Hume's principle, the very foundation of his whole argument, is actually true in the first place? Is it like a logical truth, true by definition? Or is there something more to it?
That's the million-dollar question right there. Like, if it's not a basic logical truth, then what's supporting it? Where's the grounding coming from?
Right, exactly. And it's a debate that's, still going strong today. You've got some philosophers who argue that Hume's principle is analytic, meaning it's true just based on the meaning of the words themselves, like saying all bachelors are unmarried. It's true by definition.
But then there are others who say, no, it's synthetic, meaning it's not just a definition, it's actually telling us something substantial about the world. And we need some kind of justification for it beyond just logic.
That's the key distinction, and it's not trivial. It gets to the heart of what we consider knowledge and how we come to know things. And this is where that whole debate about the existence of abstract objects comes into play.
Ah, yes, the existence of abstract objects, that old chestnut. So if Hume's principle isn't just a definition, if it's telling us something about, like, the nature of numbers, then it seems to be implying that numbers actually exist as these abstract entities.
That's the crux of it. And for some philosophers, that's a huge leap. They'd say, hold on, we can't just assume these abstract things exist. We need some serious justification, something more than just logic. We need some way to connect them to our experience of the world.
It's like asking, where do these numbers hang out? Do they exist in some, I don't know, Platonic realm of forms? Or are they somehow constructed by our minds?
Exactly. And even Frege, he recognized this challenge. He knew that his whole system depended on concepts and extensions existing. And he really grappled with how we, as humans, apprehend these logical objects.
You know, it reminds me of that Julius Caesar problem. It kind of highlights this difficulty. Can you remind us about that one?
Absolutely. The Julius Caesar problem, it's a real head-scratcher. It shows how tricky it is to categorize these abstract entities, like numbers. If numbers are extensions of concepts, like Frege argued, then how do we know that Julius Caesar isn't also an extension of some concept? How do we know what's a concrete thing and what's an abstract entity?
It's like a problem of individuation, right? How do we tell one abstract object from another, or even know what counts as an abstract object in the first place?
That's it. The Julius Caesar problem points to a deeper issue. Even if we say, okay, fine, abstract objects exist, how do we distinguish them from each other? How do we individuate them? It's not enough to just say they're out there.
It's like having this box full of puzzle pieces, but no picture to guide you. You know, there's a complete picture in there somewhere, but if you can't figure out the individual pieces, how they fit together, well, you're kind of lost.
That's a great analogy. And these questions about abstract objects, about individuation, they really go beyond Frege's theorem itself. They take us straight into the realm of metaphysics, which is a whole other adventure.
Ooh, one we might have to take on in another episode. But for now, even with these, like, lingering questions, it's hard not to be impressed by how bold and ingenious Frege's work was. It really changed how we think about the connection between logic and math.
Absolutely. He opened up all these new ways of thinking and, laid the groundwork for some of the most important philosophical and mathematical debates of the 20th century.
It's like he shined a light into this hidden world of arithmetic, revealing a structure and a beauty that we just hadn't seen before. And even if his system has its issues, it's undeniable the impact it's had on how we understand knowledge, logic, and even the nature of reality itself.
Well said. But as we all know, all good things must come to an end, and it looks like we've come to the end of part 2 of our deep dive into Frege's theorem.
We've journeyed through second-order logic, wrestled with these abstract objects, pondered the very nature of mathematical truth. It's been a wild ride. But we're not done yet. There's
Still more to uncover. Join us in just a moment as we wrap up our deep dive with some final thoughts on this amazing, influential theorem.
And we're back, ready to wrap up our Frege's theorem adventure. I gotta say, it's been a wild ride, really a philosophical roller coaster. We've twisted and turned through logic, numbers, the whole nature of knowledge.
It has been a pretty thought-provoking journey. We've been exploring Frege's ambitious project, his attempt to show that arithmetic is, at its heart, rooted in logic.
And we went deep into his logical system, right? From that second-order logic to equinumerosity. It's a lot to take in.
It's complex stuff, no doubt. But we also tackled those big philosophical questions that Frege's work brings up, like, do abstract objects exist? Is Hume's principle justified? How do we humans actually grasp these mathematical truths?
And you know what? Those questions, those are exactly what makes Frege so fascinating, even after all this time. It's amazing. He built this incredibly complex logical system, and he sparked these deep philosophical debates that are still going on today.
He was a true pioneer, that's for sure. But it makes you wonder, where does all this leave us? We've seen how brilliant Frege's work is, but we've also seen those shadows of uncertainty, those questions that just keep lingering.
Yeah, no easy answers here. It's like the more you dig into these fundamental questions, the more complex they become. It almost makes you question everything you thought you knew.
And that's the beauty of philosophy, right? It's not always about finding the definitive answer. It's about the questioning, the exploring, the refining how we understand the world and our place in it.
That's a great point. It's about that journey of discovery, the intellectual wrestling match. You push the boundaries of knowledge and embrace the mystery of it all.
Exactly. So as we wrap up our Frege's theorem deep dive, I think we should leave our listener with a final thought, something to spark further reflection.
I like it. A little something to ponder on their philosophical journey.
We talked about how Frege wanted to ground arithmetic in logic, right? But if Hume's principle, that cornerstone of his argument, isn't just a matter of definition, if it's really telling us something about the world, then how do we come to know that principle?
There it is, the big question. If it's giving us real knowledge about numbers, then what's the source? Is it experience? Intuition? Or something else entirely, something we haven't even thought of?
That's the question I'll leave you with, dear listener. What is the epistemological status of Hume's principle? How do we bridge that gap between the logical and the empirical, between those abstract numbers and our everyday experience?
It's a question that's kept philosophers busy for centuries, and it still challenges how we understand knowledge, logic, mathematical truth, the whole shebang. And on that note, I think we've reached the end of our deep dive into Frege's theorem.
It's been a true pleasure exploring these ideas with you.
Likewise. And to you, our listener, we encourage you to keep pondering the implications of Frege's work. Who knows what philosophical gems you might discover along the way. Happy exploring.